Johanna jogs along a straight path. For 0 is less than or equal to t is less than or equal to 40, Johanna's velocity is given by a differentiable function v. Selected values of v of t, where t is measured in minutes and v of t is measured in meters per minute, are given in the table above. We see that right over there. Use the data in the table to estimate the value of not v of 16, v prime of 16. And we see here they don't even give us v of 16, so how do we think about v prime of 16? Well, just remind ourselves, this is the rate of change of v with respect to time when time is equal to 16. So we can estimate it, and that's the key word here, estimate. We can estimate v prime of 16 by thinking about what is our change in velocity over our change in time around 16. And when we look at it over here, they don't give us v of 16, but they give us v of 12, they give us v of 20. So let's figure out our rate of change between t equals 12 and t equals 20. So our change in velocity, that's going to be v of 20 minus v of 20 minus v of 12. And then our change in time is going to be 20 minus 12. And so this is going to be equal to v of 20 is 240. V of 12, we see right there, is 200. And so this is going to be 40 over 8, which is equal to 5. And we would be done. It's for good measure, it's good to put the units there. So this is our rate. This is how fast the velocity is changing with respect to time. So the units are going to be meters per minute per minute. So we could write this as meters per minute squared. Per minute, meters per minute squared. And we're done. Now, if you want to get a little bit more of a visual understanding of this, and what I'm about to do you would not actually have to do on the actual exam, well, let's just try to graph. Let's graph these points here. Let me give myself some space to do it. So if we tried to graph it, so I'll just do a very rough graph here. So let's say this is y is equal to v of t. And we see that v of t goes as low as negative 220, goes as high as 240. So I want to draw the horizontal axis someplace around here. T is positive, so it looks something like that. And so let's make that 200 and let's make that 300. And so then this would be 200 and 100. 200 and 100 there, and then that would be negative 100, and then that would be negative 200, and then that would be negative 300. And we see on the t-axis, our highest value is 40. We go between 0 and 40. And so these obviously aren't at the same scale, but this is going to be 0. If we put 40 here, and then if we put 20 in between, and so this would be 10. Let me do it a little bit to the right. That would be 10, and then that would be 30. And so what points do they give us? So they give us, I'll do these in orange, 0, 0. So that is right over there. They give us, when time is 12, our velocity is 200. So when the time is 12, which is right over there, our velocity is going to be 200. So that's that point. When our time is 20, our velocity is going to be 240. So when our time is 20, our velocity is 240, which is going to be right over there. And then when our time is 24, our velocity is negative 220, so she switched directions. So when it's 24, so 24 is going to be roughly over here. It's going to be negative 220. So negative 220 might be right over there. And then finally, when time is 40, her velocity is 150, positive 150. So at 40, it's positive 150. And so these are just sample points from her velocity function. But what we wanted to do is we wanted to find, in this problem, we want to say, okay, when t is equal to 16, what is the rate of change? And we don't know what v of 16 is, but what we could do is, and this is essentially what we did in this problem, we could say, all right, Well, we can approximate what the function might do by roughly drawing a line here. So if you draw a line there, and you say, all right, well, v of 16, or v prime of 16, I should say, so v prime of 16 is going to be approximately the slope, of this line. That's going to be our best job, based on the data that they've given us, of estimating the value of v prime of 16. So we literally just did change in v, which is that one, delta v, over change in t, over delta t, to get the slope of this line, which is our best approximation for the derivative when t is equal to 16.